Reinforcement learning is often cast as the path towards human-like intelligence, thanks to its ties to gaming, robotics, and autonomous systems. But if you spend time looking into reinforcement learning, you'll notice something. People strongly disagree about whether it's actually useful. On one side, you hear about impressive successes like AlphaGo. On the other, critics argue that reinforcement learning doesn't really work in real-world applications. So who's right? In this video, I'll break down where reinforcement learning actually makes sense, the biggest challenges it faces, and what it really takes to use it in production systems. To understand when you should use reinforcement learning, it helps to go back to where it all started. RL comes from the combination of domains, trial and error learning, and optimal control. The field of trial and error learning contributed to the idea that if an action leads to a good outcome, it will be repeated, but if it leads to a bad outcome, it will be avoided. The simple concept speaks to trying many alternatives, selecting actions, and associating the actions with their consequences, all of which are key components of RL. The field of optimal control focuses on designing a controller to minimize a measure of the behavior of a dynamic system. These problems can be formalized as Markov decision processes, or MDPs. MDPs are a mathematical tool for modeling sequential decision-making problems. It introduces the idea that given my current state and current action taken at time t, the environment will transition to the next state and receive a reward at the next time step, t plus 1. The decision maker then observes the next state and reward, chooses a new action, and the process is repeated. The objective is to learn a strategy for selecting actions that maximize the expected return, which is the sum of rewards over time, typically discounted to prioritize immediate gains over distant ones. These two lines of work came together in the study of temporal difference learning, where ideas from trial and error learning and optimal control merged into a new line of work, which we know as reinforcement learning. Based on the origins of RL, we can already outline the kinds of problems this technique is designed for. First, it needs to be a sequential decision process, meaning the RL agent is taking a series of actions over time. Second, the environment the agent dwells in must respond to the agent's actions. And lastly, there must be a reward signal, which will serve as a way to associate actions to good or bad outcomes, so the system can learn from it. Now, this describes a large set of problems from many domains, and in fact, there is a large body of research showing the benefits of RL in many areas of work. That leads to the question, why not use it? There are four main practical challenges that make it hard to use RL. The first is sample efficiency. Most of the time, thousands, if not millions of iterations through the RL loop are needed for the agents to learn good behavior, which quickly becomes computationally expensive. This gets even more costly in large environments with many possible states and actions. The second is lack of generalization, meaning that agents often perform well in the environments they were trained in, but even small changes in conditions can cause performance to drop significantly. This happens because to succeed in a specific environment, the algorithm overfits to the patterns and conditions of that environment. As a result, when transferred to a different setting, its performance drops. Then there's interpretability. It's often difficult to explain why an RL agent made a particular decision, which becomes a serious limitation in settings where safety and reliability standards must be met. And finally, both training and resulting performance can be unstable. Since the data is generated online during the training phase, the action selected will depend on the randomness of the environment, its initialization, magnitude of rewards, and even algorithm implementation, meaning that two agents trained using the same algorithm and hyperparameters can have significantly different performances due to random seeds used in training and other implementation choices. In addition to these core issues, there are other practical challenges that come up when trying to use RL in real systems. One difficulty is the reward function itself. The reward function must capture exactly what you want the RL agent to learn, which is surprisingly difficult to do, and small mistakes here can lead the agent to learn the wrong behavior. Another issue is data quality. Training your agents in a real scenario might be impossible, so training is often done using simulations, but no simulation perfectly matches reality. For this reason, the agent's performance might not be as high in the real scenario. There's also environment changes. Real world systems are not static, conditions often shift over time. That means an RL agent might need to be retrained repeatedly, which adds ongoing computational cost. And unlike some other methods, RL comes with no guarantees of optimality. In other words, even if training works well, there's no promise that the solution you get is the best one. And finally, there's a deployment challenge. Even if you can train an RL agent that provides significant benefits to your problem, can you provide the agent with the information it needs in real time? To add RL to the production environments, you need to capture data with sensors, transmit it using a local network, store the data, perform the necessary computations, and have a framework to visualize the results. Without this infrastructure in place, deploying RL in production is unrealistic. Now you might be thinking, why would you even try to use RL? The key reason is that a large number of real-world problems can be framed as sequential decision-making problems or MDPs, which makes them a natural fit for reinforcement learning. And since RL agents rely on an internal representation of the environment, they do not require large datasets describing the system, making them well-suited for applications where data is limited. And importantly, once an effective strategy for selecting actions has been learned, it can be used to make decisions very quickly in real time. This is a big advantage in comparison to solving a complex optimization problem from scratch every time a decision needs to be made. So, should you use reinforcement learning? The honest answer is it depends. If your problem can be framed as a step-by-step decision process, you don't have labeled data, you need fast decisions in real time, and you have the infrastructure to support it, then reinforcement learning might be the right option for you. But if your computational resources are limited, your environment is hard to represent reliably, or you need explainable decisions, then RL is probably not the right tool. So, I'm curious, have you used reinforcement learning before? And looking back, was it the best approach for your problem?